All right, let's go ahead and get started. I do want to welcome you to this worksheet. This is factors affecting solubility. You are not going to need a calculator or a periodic table or even a solubility chart, so let's go ahead and get started. We're going to start with a fairly simple question. We want to define the term solubility. What do we mean by solubility? It's the maximum amount of solute dissolved in a solvent at a given temperature. So let's kind of diagram this. Let's say we have a beaker that looks something like this, and in the beaker we have a solvent. Water, for example. It doesn't have to be water. It can be carbon tetrachloride, benzene. There's a lot of different solvents that we could have used, but we're going to start with water. And in the water, we have a solute, right? Water was a solvent. And the solute may be sodium chloride, right? And we know sodium chloride, by the way, is going to dissociate in the water, and that's going to be our solute. The question is, how much solute can we dissolve in the solvent? Well, that's called the solubility, and it's dictated by a number of different things, but mainly it's affected by the temperature. Well, we're going to see that the warmer the temperature, the more solute that can be held by the solvent. But we'll start with our definition, and we're going to go on now to number 2, which asks us to list the factors which affect solubility of a solid or liquid. We mainly talk about solids dissolved in liquids, but liquids can be dissolved in liquids. And we'll talk about that example in just a moment. But again, I want to draw your attention to temperature, a very important factor in determining the solubility of a solid dissolved in a liquid. By the way, I did mention that liquids can be dissolved in liquids. Let's think about the example of mop water, where we have a little bit of ammonia dissolved in a lot of water. So the lesser of the two liquids is going to be the solute, the more abundant liquid is going to be the solvent. So temperature, that's the first one. The next is particle size. All right, what do we mean by particle size? Well, let's take a look at a situation in which we want to dissolve, say, a sugar cube into water. So here's the sugar cube just like that. Now, if we put the sugar cube into water, what's going to happen is that the water is only going to have access to the surface area that you see on the sugar cube, right? It's going to have access to the sides, the 6 sides of the sugar cube. But if that sugar cube was divided into, well, granules, right? Like granulated sugar, the granulated sugar is going to dissolve a lot faster. Why? Because of the fact that the water has access to a much greater surface area. So particle size and surface area are really the inverses of each other. The smaller the particle size, the more surface area that the solvent is going to have access to. So particle size is another factor that's important in affecting solubility. Next is agitation. What do we mean by that? Well, I think we're all familiar with, as children, drinking chocolate milk, from making chocolate milk with powder and dissolving it. And one of the things that we did was we agitated it. We did it with a spoon. We stirred it. So agitation, moving it around, moving the solute and solvent around in the solution are going to increase the solubility. So agitation is another important factor affecting solubility. And lastly, the nature of the solute itself. What do we mean by that? Well, we're going to talk a little bit about a term in just a few moments. Like dissolve like. Like dissolves like. What we mean by that is polar molecules are dissolved, or polar solvents will dissolve polar solutes, and vice versa. Okay? So the nature of the solute itself is also going to be a factor. Let's look at number 3. What are the factors which affect the solubility of a gas dissolved in a liquid solvent? So we have a little bit of a different situation here. Now you might say, well, wait a minute, I didn't even know that a gas could be dissolved in a liquid. Well, let's think of a carbonated beverage like a Dr. Pepper or a Coca-Cola. Those have carbon dioxide. Those are liquids with CO2 gas dissolved in them. So yes, you can have a gas that's dissolved in a liquid. Let's talk a little bit about pressure. What's the effect of pressure on the solubility of a gas in a liquid? And we'll talk about that in just a little bit more detail in a few minutes, but I just want to point out this. That if we have a liquid and we have these gas particles, I'll draw them as these little circles just like that. If I have an increased pressure, right, I'm going to place a pressure over the top of that. That's going to have a tendency to increase the solubility of the gas in the liquid, right? It's going to force gas into solution by increasing the pressure, all right? So pressure is definitely an important factor in the solubility of a gas dissolved in a liquid. How about temperature? Temperature is also important. Now we remember temperature was in our last list, but as you're going to see in just a few minutes, as you increase the temperature of a gas dissolved in a liquid, the opposite of what we just saw with a solid dissolved in a liquid occurs. Solids dissolved in liquid increase in solubility as you increase the temperature, but for gases dissolved in a liquid, you're going to decrease the solubility as the temperature increases, and we'll look at a real life example in just a minute. Let's look at number 4. What happens to a solid dissolved in a liquid when the temperature is increased? And when you're looking at these types of questions, make sure you know exactly what the solute and solvent are. We have a solid dissolved in a liquid, right? So and we're talking about temperature is increased. So remember that as the temperature is increased, the solubility of a solid in a liquid is going to increase. You can get more solute in the solvent at an increased temperature. There are a few exceptions, by the way, but for the most part, that's true. Number 5, it says, what happens to a solid dissolved in a liquid when the pressure is increased, right? So this time it's a solid dissolved in a liquid. This time it's pressure that we're looking at. Well, as it turns out, pressure is not a very important factor in determining the solubility of a solid in a liquid. So there would be no effect whatsoever. You can increase the solubility. The reason for that is solids and liquids are just not compressible. So nothing's going to happen if you increase the pressure. Let's look at number 6. Number 6 says, what happens to a gas dissolved in a liquid? So we have a gas dissolved in a liquid when the temperature increases. We're looking at temperature. And the answer is it decreases. We've looked at an example of this already. So when a gas in a liquid gets warmer, less of that gas can be dissolved in the liquid. We're through with number 6. Let's go on to number 7. Number 7 says this. It says, what happens to a gas dissolved in a liquid when the pressure is increased? So we're looking at gas in a liquid when the pressure is increased. More gas goes into solution. So we looked at that example already. So when you have a situation in which you have gas particles dissolved in a liquid, so we'll make that diagram again. You have these gas particles, right? If you increase the, let's draw some that are outside the liquid. If you increase the pressure, you force these particles that were not previously in the liquid into the liquid. In other words, more gas goes into the solution when the pressure increases. Let's go to number 8. Number 8 says, distinguish an unsaturated, saturated, and a supersaturated solution. Very simple. An unsaturated solution has less than the maximum amount of solution. A saturated solution is at the limit. It has the maximum amount. And a supersaturated solution has more than the maximum amount. You can get that type of solution by heating it up to an elevated temperature, putting a lot of solute into the solvent, and then cooling it down slowly without touching it, and you will get a supersaturated solution. Number 9, what is meant by the phrase like dissolves like? We've already talked about this as well. Polar solvents dissolve polar solutes, right? So for example, water, H2O, would easily dissolve sugar, right? It would easily dissolve sugar. But water, I'll make an arrow like this, but water would not dissolve, I'll put an X through this like this, olive oil, okay? Would not dissolve olive oil or vegetable oil or any other kind of oil, because water is polar and sugar is polar, so like dissolves like, but water is polar and oil is not polar, so it's not going to dissolve that. Likewise, nonpolar solvents, like benzene for example, will dissolve nonpolar solutes, right? So you would expect for benzene to dissolve oil, but water would not do that. Let's look at number 10. Use a colored pencil to draw a typical solubility curve for a solid dissolved in a liquid. Use another color to dissolve a gas dissolved in a liquid. I've used red to denote a solid dissolved in a liquid and green to dissolve a gas dissolved in a liquid. So notice that the solid increases. As temperature increases, solubility increases. Typically, the opposite is true of gases. As the temperature increases, solubility decreases. That'll do it for number 10. Let's look at number 11. Number 11 says, on a hot summer day, all the fish in a small farm pond are floating dead on the surface of the water. How can this be explained? Well, remember, solubility decreases as the temperature of a gas decreases as you increase the temperature. So the heat reduces the solubility of oxygen, which the fish need to breathe. So on a hot day in a shallow pond, the fish are not going to have sufficient oxygen in the pond to be able to do their life functions, right? They're not going to be able to breathe the oxygen that is present in the pond because there's diminished pressure. I shouldn't say pressure. I should say there's diminished concentration of oxygen in the pond water. They just can't survive. Let's look at number 12. It says a deep sea diver arrives on the surface of the ocean after a long dive and is found to be unconscious. What is the likely cause of his condition? The bends is the condition that we're talking about here. The reduced pressure on the ascent, remember as he comes up through the water, he's encountering less and less pressure, allows oxygen gas to escape from liquid blood. So actually in his arteries and veins, gas bubbles, O2 bubbles, are escaping. The bubbles lodge in the brain and cause the diver to pass out. It's a very dangerous situation. So divers have to be very, very careful to ascend slowly and carefully. Otherwise, this condition could occur and the diver could eventually die. Let's look at number 13. Under what conditions would a carbonated beverage quickly go flat? What do we mean by flat? Well, what we mean is that the carbonation has escaped. Two things are going to cause that to happen. The first is low pressure. When they manufacture that carbonated beverage, the liquid inside has a lot of gas, O2, or carbon dioxide, I should say, I'm sorry, dissolved in it because of the fact that they pressurize the contents of the can. Right? Also, so low pressure, by popping the tab, you're going to cause that Coke to go faster, to go flat faster. But also higher temperature. So if you open the tab and you put the Coca-Cola outside, say lay it on a hot sidewalk outside, it's going to go a lot flat. It's going to go a lot flatter, a lot quicker if you lay it on the hot sidewalk because the heat is going to prevent CO2 gas, the carbonation, from remaining in the liquid, and it's going to go flat very quickly. So that'll do it for number 13. That'll do it for this worksheet. I'll see you in the next one. Thanks. Bye-bye.